Hello, my name is Quentin Farrell, and this is my Ag Aid research presentation. Here's a picture of me. I was mentored by Dr. Cindy Grimm, and I worked under Deanna Flynn. Here is an apple tree in an orchard. Here's a drawing of the apple tree. You can see that there are some lines. They represent where branches get pruned or cut. Pruning is performed to maximize quality versus quality and to maintain fruit growth stability over time. So why is there an issue about this? Pruning is a high-skill job and requires lots of training. However, there's a lack of pruners. So our goal is to develop a tool that can teach new pruners faster. How are we going to do this? We are making a learning tool. With it, pruners will be taught essential pruning strategies and have practice making pruning determinations based on life-size digital branches. My work was curating these digital branches. So what exactly did I need to do? I needed to write a program that would take some input parameters, which represent some characteristics of a branch indicating it needs to be pruned. For example, a branch with a vigor issue, where it's too long with too few buds, or a branch with a spacing issue, where the buds are too close together. Next, I would need to somehow generate an abstract representation of this based on the parameters, and then I would need to write that to a 3D model. These are two separate steps. I decided to work with the former first, because it's hard to tell if a branch looks correct if I can't view it. So what is the abstract representation? The answer I came up with I call tubes. What is a tube? A tube is a collection of rings connected together. What is a ring? A ring is a circle in 3D space with an XYZ position, radius, and a direction. What is a direction? This one seems pretty simple. I'm showing right here. This arrow can just be considered a normalized vector pointing in the relative position from the center of the ring. In other words, from an object moved some way, then the direction is whichever way it takes to point there. Pretty simple, but what I didn't realize is that when presenting this technique, I would now indicate this simplicity as foreshadowing. Okay, what is an OBJ file? Here's the inside of an OBJ file. This represents this cube. On this first line, you can see V, which means vertex, at -1, -1, -1, which is this one right here. Here are the next three. Let's skip down to this line. You can see F means face, which connects vertices 1, 2, 4, and 3, and around all together. So basically, OBJ files are just vertices and faces connecting them. And a bunch of other important stuff, which I'm not going to cover in the interest of time. So to convert a branch to an OBJ file, all we need to do is write the vertices and faces to a file. So let's do that. So this is a segment of a tube, just two rings next to each other. All we need to do is just place some points around a ring, and that gives us the vertices. So here it is with 6 points per ring. And then for the faces, all I need to do is take two adjacent vertices on one ring and the next ring, and that becomes a face. And there we go. We have that segment completed, and we just repeat that for the entire tube, and now we have the entire branch written to an OBJ file. So, if you recall that a branch is a tube, which is a collection of rings, which are circles in 3D space, and circles have an XYZ position, radius, and a direction. Well, writing all those directions specifically can get kind of tedious. So it'd be nice if we could automatically convert relative positions into directions. So here are a bunch of points. And here's the algorithm I came up with to do that. So here are the relative positions between each other. And then in order to find the directions, all you need to do is take the average of the normalized relative positions between each other, and that gives you the directions. Nice and simple. So let's test it. So here's some testing code. It makes a tube, which is made up of rings, which have centers and have radii. And then here's the algorithm described in the previous slide to determine the directions. And then we write that to an OBJ file with 6 vertices per ring. And it's supposed to look like this based upon what the centers are specified as. And let's see how it turns out. That looks pretty good. We got all the radii correct. They're all pointing in the right directions. And they are all in the correct positions. But that doesn't look exactly right. So what went wrong? This model that we have on the left doesn't seem to have that issue, but what if this happens? To illustrate that, look at this GIF. You can see, although everything is the same, the only thing that's changing is the starting rotation around the ring of where the vertices are. So how can we ensure that the first one happens, but not the second? With only the information that we have based upon rings. Disappointingly, that's impossible. So what we need to do instead is change what our definition of ring is, not be directions, to be rotations. So what is a rotation? This seems pretty simple, but it's quite complex. There's a lot of different ways to represent 3D rotations. What we were doing before was this, except we were ignoring all these other parts and just assuming them when rings were created, which obviously caused those issues before. What I chose was to just take it easy and use a different library to handle the rotations for me called SciPy, and that worked pretty well. So now, how do we determine the rotations automatically from the relative positions? This is an algorithm called parallel transport. The first step is to use the first part of the previous to find the directions. Next, you need to basically choose an arbitrary first rotation based upon the first direction. And then you need to find a rotation from the first to the second directions. And then you can combine rotations together. So you combine the first arbitrary rotation with the changing rotation, and that gives you the rotation for the second ring. And if you repeat this for the entire process, you are able to get all the rotations. And so let's see how this works. So here's before, and here's after. Yippee, it works. So we wrote to the 3D model, and that works good. All we need to do now is generate the abstract representation. This took me 3 different attempts. First attempt in red was a parametric attempt. However, it had the issue where it doesn't point towards the sun, which branches do, so it's no good. The second attempt is in yellow, is an iterative one, but I wasn't able to configure the vigor with that one. So finally, the third attempt is in blue, which is what I'm going with. So how is it generated? So let's go step by step. So first, we place a ring somewhere, and then we move forward somewhere and place another ring. And let's just see how that looks for now. So here is showing the generation step by step. We have one ring generated, and we move forward and place another ring. So we want more than just 2 rings. So let's repeat this a couple times, and let's use some variables. We're going to use the variable named energy, which starts at some value, and each time it moves, it consumes some amount of energy. When it runs out of energy, the branch stops generating. So it looks like this. That's getting better. Now let's add in some random turning, and that's getting good. Next, let's add in splitting. And so how this works is that every time it might have turned, there's a random chance it will split instead. We're using another variable called abundance to determine whether or not it splits or not, the chance of splitting. And then we are transferring some energy from the original branch to the next branch. That way, that branches that have lots of children end up being shorter. Also notice how different branches have different radii. Well, that results in, that's because the radii is dependent upon the energy at that moment. Next, let's just add in a lot more variables and modify them in places. So now the generated branch looks pretty similar, but it is a lot more configurable now, so it doesn't have the issue of the second attempt. Next, let's apply the parallel transport described earlier. And then let's do subdivision. The purpose of this algorithm is to make the branch appear smoother. Rings are inserted between existing rings, and the existing rings are moved and resized, all to achieve a smoother result. I derived this algorithm from for subdividing tubes from the Catmull-Clark subdivision surface algorithm for subdividing meshes. Finally, we need to do simplification, which just removes rings that do not make substantial impact on the resulting mesh. And here's the result. The what variables are set at the beginning are can be configured, and so I have set those at the beginning of this GIF such that they create spacing issues, and at the end they create vigor issues. And yeah, so it's ready to be loaded in the teaching tool. There is one limitation with this thing, is that it doesn't perfectly follow directions. That's all. Thank you.